Here we are again at a point where I think a visualization in Maple will help. Now we've visualized the curves themselves, right? Previously, but now I'm going to add a little animation to each of these curves, meant to simulate what it would be like to have an object moving along these curves. Now, let me just say that the type of motion that we're looking at right now is somewhat idealized in the sense that it does not take into consideration external forces. It's simple. It's simply based on the path that this object is on. In this case, it's that little red dot. So let me go ahead and play this one, right? And there it is. So there's our object moving along this straight line. And just based on the fact that the motion is linear, you notice it seems like the speed is constant. It seems like that red dot was traveling at constant speed, right? Let's look at the next path, and this one is definitely not linear. It's kind of a spiral, right? It's kind of like a spiral. And it's going to spiral inwards towards the origin, right? You can have spirals where it's spiral outwards. This one spiral inwards. And let's play this one, and there it is. So it seems like it's really fast at the start, but then it's like in order to take all those turns, do you notice how it's slowing down? It's slowing down. It's going very, very slowly until there it is. It stops at the origin. Let's kind of back this up. Let's play this one in reverse, and I will control it. Actually, let me do that and have it go in the opposite direction. And so there it is. It's going to go in reverse. And you can see where it's slow, and then it starts to pick up speed, and then it's just going faster and faster and faster, and yep, shooting out of this world, right? So there you go. There's some nonlinear motion on a spiral. Now, obviously, you take a look. So up here, you take a look at the way I defined the curve. This is my R, and you can see it's not a trivial thing by any means, right? So to analyze this by hand will be very, very tedious. But again, that's where the power of a software like Maple comes in really handy, right? Okay, let's see. The next one is, again, linear, but this one is in 3 dimensions, right? So I just have the axes forming a box. And then let's go ahead and play this one and see what it looks like. Again, it's just, linear motion. Seems like constant speed. And if you think about, what the linear vector function would look like, when you differentiate it to get your velocity, you're just going to get constants. And then when you find the magnitude of that velocity vector, it's going to be a constant. That means your speed will be constant, right? So all the things that we do by hand with the calculus, it should make sense from a practical standpoint. Okay, so what do we have here? Oh, this one is circular, right? But it's still in 3 dimensions. Oh, where are we? Oh, here we are. Yep. So let's go ahead and play, and there it is. Now this one, definitely it's not linear, but it seems as though it is the object is still traveling at the same speed. What's really interesting, and I think it's probably going to stop here soon, but let me actually change the perspective that we have. So we're looking down on this. If I play it again, right, can you see it's just kind of going around? It doesn't seem like it's speeding up or slowing down. Well, this is another type of trajectory that we can prove mathematically, actually, that the speed has to be constant. So along lines and along circular paths, right, your speed will be constant. Circular paths that's centered at the origin, right? And let's see, our helix. So let's take a look at this one as our red dot goes up the helix. Let's see. This is still, like somewhat circular, right? But it's just that the elevation changes, so it's not like stuck in one plane. It keeps, in this case, the z value is going to increase. So it's going to go up, and it still looks, I don't see it speeding up or slowing down, right? So it looks like it's still constant speed, right? And there it is. And again, you notice what's interesting, if I look at if I change the perspective here, and then let's say I start it over, yeah, you can't tell the difference just looking down on this. You can't tell the difference between this motion or the one before. They both just look like you're moving in a circle, right? It's just that this one now, you really get a sense that, oh, yep, there is some elevation to it as well, as the z value goes basically from 0. Yeah, the z value goes from 0 up to 20, right? Okay, so what is this one? Oh, okay, so this is the one where there's no real pattern. It definitely is non-linear, right? So this would be the coaster, right? The coaster of doom. And this one, I can see where it's slowing down a bit and then speeding up. It's like it slows down to make those corners, and then it kind of speeds up along the straighter path, or the less curved path part of the trajectory. Let's see if we were to change this to get us. Let's look at it from a different perspective. And maybe I'll play this one in reverse. See, yeah, so here you can definitely see it more clearly where it's speeding up and then it slows down to go around those corners. But the thing is, those corners are nice and smooth, right? So they're nice and smooth. And even though it has to slow down quite a bit, there's nothing jerky about that particular path. Right? And then the last one, I believe this is the last one. This is the path that has the sharp corner. Let's take a look at it. And there is that sharp corner, right? So you're going to go down this hill, and then you're going to have to, somehow it's going to have to navigate the sharp corner. Let's see what it does. So I think this is probably a good view of this one. Let's go ahead and play. So it's traveling along. And you notice it literally had to come to a stop. It had to come to a complete stop to navigate that sharp corner. So it was like, so just for that second where it wasn't moving, so think about it. If it wasn't moving at all, right? It's almost like, well, in this, what happens is the velocity vector was the 0 vector. So it had no direction, no magnitude. So it literally had to come to that instantaneous pause or stop, maybe pause is a better word, to navigate it. Let's see it again. And again, let's play it in reverse so you can see. So there it goes. And then the closer it gets to that sharp corner, and there it is, and then it goes back up, right? So you can see how the lack of smoothness at that particular point, how it affected the motion, right? Just for a second, it was like the motion was directionless. It wasn't quite sure where to go, what to do. But then after that, everything else was nice and smooth, right? So, when we talk about these vector functions, it's easy to just kind of get lost into the formulas and whether it's an integral, all the techniques and the derivatives and so forth. But yeah, these can be used, and not can be, but these are used to model all types of motion. And then you analyze the motion, in kind of this simulated environment before you start building things. So you want to model those coasters, and then you measure a lot of, and then once you start taking into consideration other forces, like stresses and gravity and things like that, you want to make sure that things are safe before you start building them. But this is where it starts. The framework, right? The framework of a lot of that analysis is built on these vector functions, right? So hopefully you found that interesting, and I will see you soon. Bye.